Aloha and welcome to our video on the vast world ocean. In this video, we will recognize that most of the Earth's surface is covered by water. We'll look at the four main ocean basins, and then we'll talk about how technology has allowed us to see the topography of the ocean floor. Okay, so to begin, if we take a look at our planet, here we have a polar view of our planet. So we can look from the North Pole or we can look from the South Pole. And what we notice is we see an awful lot of blue. There's a lot more blue in the southern hemisphere than there is in the northern hemisphere. But what we notice is about 71% of the Earth's surface is covered with the oceans. So they're a very important thing to our planet. So let's take a little bit of a deeper look inside of them. Now, when we're talking about our oceans, we realize that we have four primary ocean basins, and that would be like the deepest part, the collections for the waters to be in. The largest by far is going to be this one over here, which will start on that side and kind of finish up on this side, and that's our Pacific Ocean. That's the largest ocean that we have. By size, the next one is going to be the Atlantic Ocean, and notice both of these oceans tend to extend in the northern and southern hemisphere. Remember, our hemispheres are divided by this equator here, so we can see that we have two primarily large oceans. We also have the Indian Ocean, which is over here, and while it's about the same size as the Atlantic Ocean, notice it's primarily a southern ocean. It's primarily in the southern hemisphere. And then our last is this teeny tiny little one up here called the Arctic Ocean, and that's only about maybe 6 or 7% of the Pacific Ocean's volume, so it's a lot smaller than the other three. Okay, so what does the bottom of the ocean look like? What does the ocean floor look like? Is it flat? Is it bumpy? Does it have characteristics and features? Is it just a vast wasteland? These were questions we didn't really know an answer to until about 100 years ago. Prior to that, what we did is we found our depth with soundings. So you would take a string and it would have these colored ribbons marked off every few fathoms, and they would throw that over the side of the boat and wait for it to hit the bottom, and then they would count how many ribbons had gone past or look at the color and determine how deep it was, and then they'd yell how deep the ocean was at that point. So shallow areas, it was really easy to measure depth because you could take a piece of rope with you and do this. But once we got out into the middle of the oceans, out in these areas here, it was too deep for that rope to reach. So we did a lot of observing and we did a lot of inferring and we tried to figure out what the bottoms look like. And what they felt is like if you dig a hole on the side of the beach, what you'll notice is that you kind of get this flat bottom that you see there out of the sand. And that's what they thought the bottoms of the oceans were like. So that's what we assumed it would be. In the 20s, we discovered sonar, and we used that sonar to help us find submarines. After World War II, what we did is we came back across the Atlantic from Europe. We brought our boats back to America, and as we did so, they said, hey, let's turn on the sonar and see what we can find. And as they shot down to the bottom, they found that there were these huge mountain ranges that were underwater. And they found that there were caverns and canyons underwater. And we noticed that the bottom of the ocean wasn't flat at all. In fact, it was covered with all kinds of topography. And we did this by sonar initially, and we've had more developing technology, and we'll show you this a little bit later on in the video. But this is how we discovered this mid-oceanic ridge that we see running down the Atlantic. And we see another one over here in the Indian Ocean. So we've seen that there are topography, there's things on the bottom of the ocean. So it's not that flat wasteland that we used to think, but instead it's this topographic rich area. Okay, let's talk a little bit about this sonar and how it works. Now, with sonar, what we have is we have a ship here, a vessel, which is going to emit an outgoing signal. It's going to create a sound and send that sound wave out from the boat. And you can see that sound wave traveling from the bottom of the boat down to the bottom of the ocean there. When that sound wave hits the bottom of the ocean, it's going to bounce off the bottom of the ocean, and we create what we call a reflected signal, and that reflected signal is going to bounce back up to the ship. And that allows us some very important information. What we can do is figure out the time that it takes for that signal to bounce from the ship down to the bottom of the ocean and back. So we're timing it from here all the way till that signal gets back to the ship. When we have that time, we're going to divide it by 2. And the reason we divide it by 2 is because that sound has traveled all the way to the bottom and then back all the way to the top. So it's traveled that distance twice. When we divide it by 2 and we multiply it by the speed of sound in water, what that gives us is the depth of the ocean. And that's quite simply all we're doing to find the depth using sonar. Now, recently, we've worked on sonar, we've gotten better, and instead of having just this single ping that goes down and comes back up like we see here, we can have a multi-array beam. So we'll send out actually multiple beams of sound this way, and then they come back, and that allows us to paint a bigger picture of the ocean floor. So that's how we use sound to map the bottom of the oceans. And that worked for us for a long period of time until we discovered another method. Our current method of mapping the ocean's floors is done with a satellite. And that satellite, as it's orbiting around the Earth, is going to send down a radar pulse. Now, sonar uses sound, radar pulse uses radio waves. And this radar pulse will come down just like it did from the boat, and then it'll bounce back up to the satellite. And once again, we can calculate the distance and all of that. But what we're looking for is we're looking for this change in elevation of the surface height. So we're looking at the ocean over a broad area and seeing how that ocean is distorted. And that ocean gets distorted based on what's on the bottom of the ocean. So if the bottom of the ocean has a mountain, let's say, on the bottom of it like this, what we'll notice is that the ocean's surface will kind of go like this, and it will bulge over where that mountain is. And that's what our satellites are able to check. Our satellites will be out there, and they'll have the ability to go through, and they'll send down this radio wave, and they'll measure that there's this slight gap here. And by doing this far enough and knowing how tall one of these is, we can extrapolate that information out, and that's how we make our current maps of the ocean floor. Okay, so that's it for our Vast World Oceans video. As always, good luck on the lessons and the quizzes, and we will see you in the next video. Aloha and welcome to our video on the ocean floor features. In here we will discuss the three main regions of the ocean floor. We'll talk about continental margins. We'll explain the formation of new ocean floor at deep ocean trenches and abyssal plains. We'll revisit the idea of seafloor spreading, and we'll revisit the hydrothermal vents as well. Okay, so when we're talking about the ocean floor, we've broken that up into three major regions. The first one is this continental margin here, and that's going to go from the edge of the continent out a little ways. And we'll talk about where that distinction is in the next slide when we talk about the continental margins a little bit more. We also have these mid-ocean ridges, and here in the Atlantic we notice that we have this mid-ocean ridge out here in the middle of the Atlantic, hence mid-ocean. And then the third and final area of the ocean floor is what we call this ocean basin floor. And that's going to extend from the continental margin out to this mid-ocean ridge. So if it didn't have a mid-ocean ridge, it could extend all the way across to the continental margin on the other side. So we can kind of see that in our picture down here below, but we'll explore this area, this continental margin, in the next slide. Okay, so let's talk about the continental margin real quick. In our picture, our continental margin is going to extend from the beach, and it's going to go out into the abyssal plain a little ways. This continental margin can be broken down into three different regions, so let's take a quick peek at those. The first one is this continental shelf, and that's going to be this shallow part of the ocean that's right up next to the continent. It's going to decline a little bit, but it's not super steep. It's just kind of a gradual decline, but it's going to be marked by a shallow ocean. And this area is where we have a lot of productivity. This is where we do the bulk of our fishing. So they're very important regions. Now, the continental shelf gives way to what we call the continental slope. And this is going to be where we have a down steepward progression of the ocean floor. And that's going to take us down to about the abyssal plain. Before we get there, however, we do have this continental rise, which is going to be a gradual sloping again. So if we add the continental rise, the continental slope, and our continental shelf together, that's what we get as our continental margin. And these areas, like I said, are very productive. They're economically important. So they're very important areas to know the ecology of, but also the economy of. Now, one of the key features of this continental margin are what we call submarine canyons. And submarine is exactly what it sounds like. Sub meaning under, marine meaning water. So these are our underwater canyons. And they're created in much the same way that our canyons are created out here in the desert. And what we have is we have this turbidity current. And this turbidity current is just going to be an area of water which is nutrient rich, which makes it dense. And because it's denser than the salt water, it's going to want to go down. It's going to want to sink through the salt water. And it flows much like a river would cutting into the continental shelf and forming these submarine canyons. Now, not to be confused with a canyon, we can also have these submarine trenches. And here we have the Puerto Rico Trench, which we can see in the picture here. And what this is this is where we actually have a plate that is being subducted or going under another plate. So in this case, it's the North American plate and the Caribbean plate. They're interacting in a subduction zone. And because of that, what we're seeing is this plate's more than likely traveling down under, and it's causing the volcanic activity that's going to form some of these Caribbean islands. We can see another example of a trench, and that would be the Mariana Trench, which actually marks the deepest part of the ocean, which is what we call the Challenger Deep. And if we were to set Mount Everest in there, it still would not reach sea level. It would be entirely submerged. So that's how deep these trenches can get. The Challenger Deep is 11,000 meters below sea level. Okay, so it's the deepest part. Mount Everest, on the other hand, is only about 8,800 meters above sea level. So you can see that the oceans are deeper than the mountains are taller. Now, when we get out into the abyssal plain, one of the things we notice is we get out there, we see that it is going to be kind of this flat wasteland. And the reason we call it this flat area is because, quite simply, you can see we have the topography underneath. We can see that the oceanic crust is going to have this topography. We're going to have mountains, we're going to have valleys, we're going to see all of the same topography. The problem is we have these layers of sediment. So over millions of years, we have this sediment flowing into the ocean, and that's when we go back to our little sand example that we showed earlier. When we dig a hole on the beach, what we notice is the bottom of it is going to be flat. And if you tried to build a sandcastle underwater, that sandcastle would just kind of level itself out due to the motion of the water inside of the hole. And that's what we notice here in our oceans. At the base here, we have all of the sediment that's just going to lay down into these layers. So when we get to the bottom of the ocean, it looks to be kind of flattened out like this. And the reason for that is just all of this sediment has leveled out. Okay, so let's talk about some interplate underwater geology here a little bit. We talked before about a hot spot. That's an area where you have this magma plume that's rising up to the surface, and it can form a volcano in the middle of a plate. And the Hawaiian Islands are a great example of this, where we have this hot spot, it's forcing magma up, and we're going to have this volcanic activity. We can have an underwater volcano, and eventually, if it breaks the surface of the ocean, we end up with a volcanic island. Now, this volcanic island, once it moves past the hot spot, it's going to change its geology a little bit. And we're going to talk about the 3 different paths that it can take. The first one is going to be this one right here. It'll turn into a sinking island. And remember, we have this huge volcano that's sitting on the ocean crust. What's going to happen is that's going to cause it to push down that added weight, and it's going to actually sink down into the crust. It'll cause the crust to sink down as well. So that's what we call it, as a sinking island. If that continues over time and we get weathering and erosion, we can get a flat top. And if we look over here, we can see that it's this flat-topped underwater mountain, and that's what we call a guyout. So once it moves over the hot spot, weathering and erosion can take in, it'll sink a little bit from the weight, it'll flatten out at the top, and we end up with a guyout. Now the next thing it could do, a little different path, is this one here. And this is where we see this growth of coral and this reef around the sinking island. So we have the sinking island again, but we're going to have this barrier reef of coral. And you can see in the side picture, we can see this coral is growing up on the sides of the slopes of this mountain. So as it's sinking down and the coral's still growing, it's going to do that until we see that the island itself is sunk below, and we end up with this ring of coral we call an atoll. And inside is going to be our lagoon, and it's generally going to be a very sandy bottom, nice interior lagoon with a coral reef all around it, and that's what an atoll is. And then our third is if we don't see anything really much happening and it just kind of sinks down below the surface, then we end up with a seamount. You can see it here, but we can also get seamounts if the volcano moved past the hot spot before it had a chance to break through the surface. So these are our 3 different paths that a volcanic island can take. Okay, so let's talk a little bit about oceanic crust. We can form new oceanic crust at regions of seafloor spreading, and we talked about this one. This is where we have two plates, and those plates are going to be moving away from each other, so it's a divergent boundary, and this allows magma to rise up, and the formation of new rock, new crust material is formed that way. So this is how we make new ocean floor. Now remember, the Earth isn't getting bigger, it's staying about the same size, so that means that this plate, as it's moving away, ultimately somewhere is going to have to be subducted. And as it gets subducted, the plate melts away and we get a little bit of volcanic activity going on. So this is how the Earth maintains its size, but we can form new oceanic crust here because of seafloor spreading. And then as that seafloor is moving across this way, ultimately it'll get subducted down and the Earth stays the same. But this is how we can make new seafloor. Okay, let's talk a little bit about a hydrothermal vent. A hydrothermal vent is where we have this magma here below the surface, which is going to be heating up everything, and we'll have a little area where it's broken. Now, it's not going to necessarily be a volcano because we're not going to see magma rising, but instead what we're seeing is this pulling in of ocean water through the bottom. It gets superheated, pops out through the top here into what we call a black smoker. And within a black smoker, we can see that there is an abundance of chemicals. We have carbon dioxide, hydrogen sulfide, methane, iron, magnesium. So we're seeing a lot of minerals. It's a kind of a chemical rich water that's coming out here. And you can see the reason we call them black smokers is because that's what they look like. There's this big cloud of black smoke kind of coming out of the bottom of the ocean floor. And we found that there are actual bacteria that can take some of these chemicals and through chemosynthesis create food, create sugars, much like plants do with sunlight. Okay, so that's it for our video. We'll go into some of these topics a little more in detail in the lessons. As always, good luck on your quiz, and we'll see you in the next video. Aloha and welcome to our video on seafloor sediments. In this video, we will list the three types of ocean floor sediments. Then we'll describe the formation of all three, being terragenous, biogenous, and hydrogenous sediments. Okay, so let's talk a little bit about ocean floor sediments. There's three different kinds. We can see two of them pictured here, and we'll talk about the third one at the end. The first are what we call terragenous. And genus means that it was born of or created from, and terra is going to be land. So these are going to be the ones that are made up of rock, basically. And what we have is two different kinds, and it's based primarily on the texture or the size of the grain that makes it up. We're going to have these coarse near-shore deposits, and that's going to be things like sand and gravel. And then further out, we'll have this fine clay and mud type of sediments as well. But these are terragenous in nature, so they come from rocks. It's the base up, ground up minerals and rocks and things of that nature, and that's what makes this sediment. Now, the next type of sediment is what we call biogenous. Biogenous means that it comes from life. So there's two primary types of biogenous sediments, and it's going to be based on the material of them. We have silicaceous ooze, and then we have this calcareous ooze. The calcareous ones are going to come from shells. So it's calcium carbonate like you'd see in a seashell, and are in corals. And what you're going to see is this material is just kind of eroded away, weathered down, and it's going to be an ooze or a sediment made up of these materials. We can also have a silicaceous ooze, which is going to come from the shells of diatoms, which are microscopic little marine organisms as well. But instead of having a calcium carbonate shell, it's one that's primarily silicone. And then the third type of seafloor sediment is what we call hydrogenous, and that's going to come from the water. And this is where we're going to see things like our manganese nodules that are going to form that you'll learn about a little bit in our lesson. And these are going to be these precipitates that come straight from the water. So we can have stuff that's trapped in the water and it'll precipitate outwards. So it comes from the water, hence the term hydrogenous. Okay, so just to summarize these, let's take a look real quickly. We have our three different types. We have our terragenous sediments. The origin of that is going to be land, and those are going to be primarily from the rocks, made up of rocks and minerals, and that would be like a gravel or a mud sediment that you would find out there, and it's going to be made up of these minerals. The next is the biogenous. Remember, biogenous comes from life, and this is going to be our calcareous ooze made up of shells, or our silicaceous ooze, which is made up from the shell of diatoms. So this is just going to be further classified by the chemical nature of what the shell of the organism was. And then our last is going to be these hydrogenous, and hydrogenous is going to come from the water. And this is where we talk about things like manganese, which will precipitate out of the water into nodules. And we'll see some of those a little bit later on in these lessons. Okay, well, that's it for our video. As always, good luck on your quiz, and we'll see you in the next video. Aloha and welcome to our video on resources from the seafloor. In this one, we'll look at our resources primarily used for energy production, and then we'll look at some other types of resources as well. Okay, so let's talk about energy resources that we can get from the ocean floor. These are important because there is an awful lot of money involved in this. And most of the energy resources that we're talking about are oil and natural gas. And these are the things that we can actually drill for and extract from the ocean floor that way. There's another one that they'll talk about in the lesson, which we call a gas hydrate. And a gas hydrate is going to be a little bit different. And what we notice is we'll have these gas molecules, and you can see them here. And there are also these green molecules you see down in this one here in this picture. But what happens is you'll have these gas molecules, and they'll get surrounded by super cooled water, water that is super cold. And the interaction between the two and a little bit of pressure and a little bit of more cooling, and what we end up with is ice formation. And this ice formation will occur around the hydrate. So now you have this gas molecule that's trapped inside of this ice shell. And these are ways that we can get these gases out, like methane and things of that nature. The problem is when you release the pressure or you warm them up a little bit, this ice here is going to melt rather quickly, and it releases the gas outwards. So not exactly the easiest thing for us to do, but it is a possible source of methane that we could use later on. But far and away, the most important resource that we get from the ocean floor is going to be used for energy, and that's going to be in the form of these fossil fuels of oil and natural gas.